Chiamaka. Pardon me if I don't pronounce your name very well. And I'm only seeing 9 persons, which should be 25. I can see Brett, Damola, Jade. If I don't pronounce your name very well and you'd like to correct me, just feel free to say so, okay? Josh, I can see you. Michael, Share. Oh, yeah. So we are 10 now. By 10:40, we should begin our class, okay? So let's give a few minutes for some of our participants to join, all right? Okay.
Will you post the PowerPoints for us?
Yes, it's on Moodle already. The PowerPoint version, the PDF version, and the link for the class. Those are the first 3 things on Moodle.
Okay, thanks.
Have you checked the Moodle page?
Yeah, it's so new. I'm like struggling to go around it.
Okay. Good to see your face. Mitchell, Danny, Kate.
Good morning, how are you?
I'm good.
I was going to ask if it would be possible for you to post the questions for assignment 1, just because I'm still waiting for my textbook, even just for the first assignment, just because I don't know if it's the bookstore that's backed up on the textbooks or what's happening there.
Okay.
Yeah, I'm working on mine too.
All right, I'll do that. I included it in the PowerPoint, but I'll find a way to extract it and put it separately, okay?
Thank you.
You're welcome. Okay, I think we have about 70% of us here already. So in the next 2 minutes, we should begin our class, okay? Can you see the PowerPoint? My screen shared? Okay. All right. I welcome you all to today's class. I'm Charity Adeze Nemue, and I'd like to be addressed as Dr. Charity. Right? I think that will be easy for everyone to pronounce. But if you want to call me by my other names, you can just add Dr. Adeze or Dr. Edemue. Okay? All right. So on the module, I've posted a course compact, which is like the outline for the course. And I put the breakdown for the reading of the course there. And I don't know if we've all seen it, a PDF file called Course Compact. How many of us have seen that? You can reply by saying yes on the chat if you've seen it. Okay. All right, great. So many of us have seen it. Nice. Okay. So somewhere on our chat, I requested that every one of us should introduce ourselves before we meet today. Some of us did, while a number of us did not. But I want to assume that make excuses for us for our inability to do that, right? Okay, so get to know each other and see more of ourselves in our practical classes for those of us that will be partaking in the practicals, because some of us will not. Okay. All right, so like I've said, I'll be your instructor for this semester for General Physics 1, the 74151. If you cannot hear me, please, you can turn on your mic to call me back to say, I didn't hear what you said. I know some of you may find it difficult to hear me because of my accent. I may pronounce some words differently from what you used to know. If you miss it or don't get what I'm saying, just feel free to call me back, all right? But let's be moderate about that as well, okay?
Somebody's microphone is on and it's causing a lot of feedback. So can you please turn it off if they're not using it?
Please mute your mic. Okay, thank you. I think we are good now, all right?
Yes, thank you so much.
You're welcome. Okay, so our first class is the introduction to what we'll cover and a brief of what we'll be doing for the term or for the semester, all right? So first, I'd like to describe the reading of the course. We already know that we'll be using the college physics authored by Knight, Jones, and Field. And we'll be covering from chapter 1 to 13, okay? So the reading of the course is going to be a chapter per week, all right? So we'll have active weeks 13, and by week 14, 15, I think we'll be taking our exams in week 15, and then week 14, we'll have revision and kind of question and answer sections and all that to better prepare us for the exams. So that will be the reading of the course. We'll be taking one chapter per week, and we'll be having 3 contacts in a week outside our practical classes. All right. So we've already seen the timetable. We'll be meeting Mondays, Wednesdays, and Friday. We'll have 50 minutes classes, and that's that about the reading. So go straight to the business of the day because we'll have just a few minutes to do that. Can you all see my screen? Okay. One moment. Okay. So I believe that we all know what physics is. If I ask us to define what physics is, we know what it is. And I can see. Can you still see me? Good. Okay. So just for the sake of reminder, and for some persons who have not really interacted with the definition of the word physics, we'll just look at that as way of introduction. What is physics? This is a physics course. We'll have several physics courses at first year. But physics generally is that part of science that attempts to describe the world around us in a fundamental way, okay? It tries to do that by following 4 basic steps. And these 4 basic steps, they attempt the scientific trend, all right? But before the name scientific trend came, it was simply by observing the world around us, observing how things are changing, experimenting, and trying to build powerful predictions, trying to observe, point out, or identify patterns. Okay, so how this is done, first by observation, then by hypothesis, then experimenting, refining the hypothesis that brings about the theory we study now in schools. Okay, and that is why we'll have revised versions of textbook. The textbook we're using the 4th edition now. We have the 1st, 2nd, 3rd, because science keeps evolving. All right. So in this course, the General Physics 74151, we'll begin gradually, then we'll go into the deep waters. Not difficult, but just a step at a time. We'll get to understand how the science or the physics around us. So we'll begin by studying motion, which is the first thing that anyone can observe. So when you make statements, you woke up this morning, you made motion. Every day, you take a walk, you run, you throw things, you lift things. Those are motions, all right? And then we'll have the physics way of describing that. So we'll begin by describing motion, a representation of motion, and how we can use numbers and units to describe motion, all right? So we'll look at how to describe and explain motion, starting from the presentation of motion, all right? So this course objective is just, we have 4 basic objectives. First, to understand the translational and rotational mechanics in fluids and heat. Then to develop problem-solving skills, all right? We'll be solving some problems in class, we'll have assignments, we'll have practicals. Also to improve our communication skills. Now, when we say communication skills, we're not just talking about interaction or talking, we're talking more of in the scientific terms, all right? So when we speak scientifically, it will be different from somebody who did not enter this physics class, okay? So we'll have the scientific way of describing things from the normal, everyday way, okay? And then the 4th objective will be to enhance our physics practical skills. And this will come to play for those of us that will go into researches, engineering, we'll be doing so many laboratory work, and this will just enhance such skill for us, okay? So basically this course is not a calculus course, all right? So, but we'll be covering topics in classical mechanics and thermodynamics, and we'll be emphasizing more on the application of physics in life sciences, okay? Are we together? All right. So the topics we'll be covering, like I said in the introduction, when I was talking about the reading of the course, I'll be having chapter 1 to 13, and we're taking 1 chapter per week. So we'll have from week 1 to 6, we'll cover translational kinematics and dynamics. 7 to 8, we'll take rotational kinematics and dynamics. And then we'll take the work and energy. We'll move to fluid statistics and dynamics, then introduction to thermodynamics. And that'll be about our last topic for the semester, okay? In between the weeks, we'll have assignment, we'll have our test 1, test 2, mid-semester exams, and all other activities, including our labs, all right? So having said that, that will be covering one chapter per week. That means this week we'll have just 2 contacts to cover chapter 1. And thank goodness chapter 1 is just introduction. basic stories about how physics evolved in motion presentation, the representation, and all that, okay? So move quickly to our very first topic, translational and rotational kinematics and dynamics. Now, looking at this topic, we can relate more with the word translational and rotational, but kinematics and dynamics will sound not new totally, but how do they connect, okay? So when we say kinematics, what do we mean in physics? Because we have words that will take different meaning in the description of that words in different frame or subjects, okay? So the word kinematics came from the Greek word kinema, which in the English version means cinema. The Greek word kinema means movement, and the English version is cinema, which is motion pictures, okay? So that automatically tells you that kinematics is actually going to be talking about motions, but not in all its totality, okay? So kinematics is a branch of physics that talks about the classical mechanism that is concerned with the geographically possible motion of the body. That is the motion of the body without considering the forces involved. Okay, so whenever we say the word kinematics, we are referring to motion that disregards the effect of forces. Okay, and that is where it is different from the word dynamics. So because we'll be looking at motion from the kinematics angle and from the dynamics angle. So when we are looking at it from the kinematics angle, we will not be factoring the force causing the motion. But when it comes to dynamics, we'll be looking at it in relation to the force that is causing it, okay? So we'll be studying motion in two ways. Motion without the force causing the motion, and motion with emphasis on the force causing that motion, okay? So anytime we talk about motion, just in your head, divide it into two. Are we describing this motion with the force causing it, or we're not considering the force causing that motion? All right, so that is what we mean by the two words, kinematics and dynamics. All right, so first we'll now begin with the description of motion without the force causing it. Then we will now graduate into the description of motion. That is how the textbook chapters are arranged, all right? From non-disregarding force to involving forces. So the aim will be in studying the motion with kinematics will be to provide a description of the spatial position of the body, that is understanding the exact position of a moving object per time, okay? So we'll talk about the rate at which the particles are moving, which is the velocity, and the rate at which the velocity is changing, which is acceleration, okay? So I want to assume that we can define easily what the word velocity is and what acceleration is. They are simply by words because we have the mathematical formulas for them. Velocity is the rate at which a particle is moving, okay? And then acceleration is the rate at which the velocity is changing, okay? We'll see the formula for both velocity and acceleration later in this course, all right? So when we want to talk about disregarding the causative force that is causing a motion, we try to describe that motion considering the path that the motion is taking and its shape, okay? And this is what helps us to classify the types of motion we have, which will be seen later. All right. So we'll have motion taking a straight path, and we'll have those that are taking a curved path. We'll have those that will be spinning around its axis. Okay. So from this description, the kinematics observation of motion, we were able to classify the types of motion. Okay. And we'll be seeing that later. So before we start considering calculations, that is bringing in velocity, forces, we want to familiarize ourselves with how we can visualize motion. How we can visualize motion. And that is what the chapter 1, the first thing you see in chapter 1, representing motion. How do we visualize a moving object? Now, we often do this with two basic steps or processes. First is to develop a simplified presentation of this motion so that the key element can stand out. All right, when you see a motion, what can you see about that motion? What can you say immediately without having to think about physics and its formulas? All right. Then the second is to analyze that motion with the language of mathematics. Okay. So these two processes will be involved in the study of motion that we'll be looking at. So we'll look at the basic concept. These two processes give us the idea of this basic concept, which helped us to define motion. So we're talking about motion, motion, motion. How can we define it? Motion is defined as the change of an object position or orientation with time. Okay? The change of position or an object's orientation with time. For example, all object that moves like car, bicycle, anything you can think of that can make motion is changing position with time. It's changing orientation with time. And the path it's taking is what we call the object's trajectory, which is the path along which the object is moving. We call that trajectory, okay? So that brings us to the 4 basic types of motion, okay? And these are classified by the orientation and the trajectory of motion. So we'll have the first one, the straight line motion. We have already established that any object that is changing its position or orientation over time is making a motion. And it's taking a particular path that we can call trajectory. Okay, so the 4 classes or 4 types of motions are the first, straight line motion. Object that is taking a straight path. Object whose trajectory can be described with a straight line or straight path. Then we have the second class, the object that is taking a curved path or taking a circular motion. Then we have what we call the projectile motion. That is objects that are undergoing free fall, mostly in the air. Okay, so motion of object in the air is called the projectile motion. Then we'll have the last one, which is the rotational motion. That is motion of object that is spinning around its own axis. And we'll have so many examples of that in the solar system and in some games, right? So those are the 4 basic types of motion. Are we together? Can everybody hear me?
Yep.
Okay, good. Okay, so this is just a picture, a pictorial representation of the 4 types of motion. We can see the car on the straight path, and we can see the bike man taking the curve path. We can see the projectile motion that is throwing the ball into the air and the ball taking the projectile path to land. We'll see the rotational motion, an object rotating around its own axis. Okay, so now, having known these 4 basic types of motion, how do we present them? When we say motion is an object changing its position per time or orientation, how can we represent this motion? Okay, now let's imagine you're standing beside a moving car on a straight road, and you choose to take pictures of that car that is in motion, and you're taking these pictures at constant intervals. Let's say you're taking it every 2 seconds. You took the first one, the next 2 seconds, you took the next. Like that, you have several shots, right? That is the kind of picture we see here in figure 1-2. You see the first picture was taken, then the second, the third, the fourth. Then on the figure 1-2B side, you bring these 4 pictures taken at different times, put them together on a plane. That is the image 1 for the first car, image 2, 3, and 4. Place them because that car is on one straight line. All right. So you have the first, this tallies with this tallies with this tallies with this, and the last tallied with this one. Okay. So when we bring them together, we can easily see how that object is changing its position over that constant interval. All right. And we can easily see from this picture that we'll put together that because we took this picture at constant interval and this car is moving at a constant speed, we can see that the spacing in between, they are even. Can you observe that from this image? How many of us can observe that? I like to see, I like you to react on chat, say yes if you can observe what I'm saying. I'm waiting for a response. Great. Okay. So we see this is how we present or we represent motion most of the time. We'll take the several pictures or observe at different or constant intervals, a particular motion, then bring them into one picture to be able to interpret what that motion is saying, because the picture will tell us a lot about that motion, and we'll understand as we proceed how we'll be able to understand what a motion diagram is saying by just looking at the diagram, okay, or the picture. So we'll have this picture here that was taken 4 times on one plane, and we are seeing that they have the same amount of time elapsed in between, and then we'll have constant spacing because this vehicle is moving at a constant speed. All right. So we have, having known that this is how we came about these different kind of pictures, the represented several motion pictures in one plane. So we should understand that in this next slide, these are several motion pictures put together in one plane. All right. So we can see that from the motion pictures, we'll be able to say different things about that motion. So we'll look at the first one in A. We can see that the ball is stationary. We can, if you take the picture of a stationary ball at different intervals, just keep taking the shot, snapping, you will see that when you bring the images together, the ball will still be on the same position, right? It will not change, it's just there. So we'll say that that kind of motion is stationary. It's not moving. So a stationary ball on the ground, that is what we have in figure 1.3a. Then we look at figure 1.3b for the boy on a a skateboard rolling down the sidewalk. We can observe that this boy's motion is constant. The speed is constant. Why? Because we can see the even spacing. The space here and this, they are equal. That tells us that this boy is moving at a constant speed. Okay, this boy is moving at a constant speed. The first one is stationary, and the second one is moving at a constant speed. So let's move to the C, description of motion. The same motion taken at a constant interval, when put together, we can see the image is saying something. The image is showing that the sprinter starting for 100-meter dash race started slowly and moved faster. These pictures were taken at constant time interval, all right? Like we described earlier. If you take the first one, you can see the first image is closer to the second image, because the closer the image is, it means the slower the speed, all right? And the next image is further to the next, and this is the farthest. That means the object is speeding up. It's increasing in speed. Started slowly, increased in speed. So with this understanding, we look at the D image. We'll see that the image of the car at the beginning, the space is wide, high speed, and then it's closing up, and it came to a stop. So we see a car stopping for a red light. It's coming with a speed, and it's slowing down, and it stopped as the picture depicts. Okay, so it is decreasing the distance, that is slowing down, and increasing distance is speeding up. So we'll see the next, the figure 1.3e. For a projectile motion, a basketball thrown freely from a spot into the basket. Okay, you can see that the spaces, they are the same. So we can say that it moved at a constant speed, but this is a more complex description of motion, because we have to best describe this with figures, which we will look at later, all right? But this is just how we can use pictures to describe motion, okay? So Chiamaka said, we can say that the car is decelerating, right? You are right, the car is decelerating, okay? So I didn't use the word acceleration and deceleration because I'm yet to get to the description or definition or study of acceleration and deceleration. So I'm trying to use the description of motion picture words, all right? But we can say, you're right, we can say it is accelerating, it is decelerating, decrease in speed, increase in speed, all right? So this is just a pictorial representation of motion diagrams and how we can interpret it. Now, it's not going to be easy to always have to draw a car, draw the person, to the diagram of the leg, to the back, no. So in order to increase the speed, we found a better way to describe this motion. And we call this better way models and modeling. Now, the concept of models and modeling is to use something to represent a whole, okay? In the case of description of motion, we use a dot or arrows to represent the entirety of that object, okay? So down this slides, I put the first assignment, which is you should describe the two types of model. You see the assignment later, right? So we have models and modeling. For example, when you want to describe the motion of those cars, you can just use points, dots to understand the simple oscillation system of that motion or the orientation of that particular motion. So we use models to brush aside the complicated details and take the experimental part or points that will be of use to us, that will easily help our understanding instead of having to bother ourselves with how do we draw a car to say this car is moving or that, if we don't have pictures or cameras to just take the image of a real car. Or when we have a motion that is described with words and want to put them in the representation, how do we say, oh, a car is decelerating, can you give me the pictorial diagram, and then you start drawing cars? No. So we use models to brush away those complications and to make the understanding of our representation easier. So a model is a highly simplified picture of the reality. That is, we can say a whole car represent the whole car with a dot. All right, by the time we start seeing the pictures of what we mean by model representation, we'll understand that. So I said the basic thing that model helps us to do is to make the complex situation simple so we can think in the right frame, all right? So we have two types of models. We have several forms of models, but they are classified into two broad classes or types. We have the descriptive and the explanatory model. The descriptive and the explanatory models. As the word can clearly state, one is describing and one is explaining, okay? So we want to apply the idea of model to describing or representing a motion diagram. So we see in this figure 1.4, the first one is the diagram of the picture. What can we say about this picture? I'd like you to say something about the picture you are seeing. What can you say? What can you say about the speed of the car? Is deceleration. Great. It's slowing down. Yes. Thank you. So we can see that the car is slowing down. It's coming to a stop. Now, let's look at the model representation of this same motion. Like I said, we want to use a single point as the entirety of this object. That is just what we mean by model, okay? So we use a single point to represent the car. So the car is at point 0 here. The next one, point 1. The next, point 2. And the next, 3. You can see that this is less complex to represent when you have this description in words and you have to bring the pictorial representation. Instead of having to draw cars, you just do the dot, 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 okay? And you can as well see that the distance between this first dot and this next one is wide, it's decreasing, which tells you that it's decelerating, it's slowing down in speed. So that is the whole idea of model, or in this case, we term it particle model. All right, because we use just one dot or one point to represent the entirety of a system. Okay. So I haven't covered the representation of motion. We know how to make motion pictures, how to analyze the pictures, how to use models to represent the motion. We want to move quickly to what we call position and time. Remember the definition of our motion. We said that motion is an object that is changing its position over time or changing its orientation over time. So what do we understand by the word position and time? It tells us a lot in physics. This simple word position and time means a lot. So just pay attention to it, because as we move further, we'll be meeting position and time in different ways. Okay? So now to understand the motion of any object, we have to know its position over time. From the definition of motion, it's changing position over time. So let's take this figure that we can see here as an example. This is somebody running. It's starting. We just say, okay, this, to use this to represent the distance is going to cover in meters. We'll have the model representation of this. We'll look at them later. All right. So this is the symbol or coordinate used to represent the position along this axis. We'll have it graduated in meters. So it starts at 0. It starts racing and it's increasing, covering larger distance over time till the runner came to the finish line at 50 meters. We have been able to add or try to measure the position of this runner over time. So let's say this runner started at time t here. As it's moving, let's say we're measuring this time in seconds. Each point or each position are measured in seconds. It's moving, it's covering distance over time. You can see that. And one thing to note about this is it's a one-dimensional motion. That is motion represented only in one direction. If we want to say it in the Cartesian coordinate language, we say it's moving only in the S direction or Y direction or Z direction, but we know it's moving only in one direction, okay? So in describing the same picture, bringing in, we have described it with position. It's at 20 meters from the start, 40 meters from the start. How much time did the runner spend to cover 20 meters? So we'll bring this same picture here in our model idea. We'll find it interesting to see that from this first, from the model dots, you can already see the speed. You can describe it that is coming to a stop. It started from time 0 seconds and it came to a stop at 8 seconds. Isn't that interesting? To be able to describe a simple motion with a dot, and we can say a lot about time. So if at 3 seconds, you are asked to identify the position of this runner, you'll be able to tell, if you bring this into this, that, okay, this runner covered 10 meters at 3 seconds. So we are able to describe the position and the time spent to cover the position with the idea of position and time in the description of motion, okay? So that will take us to a more interesting and scientific description of the change of its position, not just change over time as the motion definition says. How can we bring this to defining an entire process of change of position or motion made? So it brings us to this new word called displacement. We use the word displacement every day. It doesn't mean a different thing in physics, but the description in physics has, let me say, we have the numerical and formulas to it, okay? Remember we said we have 2 ways to describe motion. We'll try to describe it visually, then we'll put a number and unit to it, which is the mathematics, all right? So you take this whole thing like a story. This is how I started, and this is what I'm introducing. Each slide is going to introduce us to a new term, all right? So we want to look at the word displacement, which means the change in position of an object as it moves from initial position to a final position. And we can easily represent displacement by, if we use S to represent the position of the object, I to represent the initial state, and the F to represent the final, all right? So you have X, I to be positioned at the initial, and XF to represent the final. So the displacement will be the change in the position, which is simply equal to the final position minus the initial position. All right, so we'll have delta X, or change in X, is equal to XF minus XI. This is the formula for position, for displacement, sorry. Okay, the change in position. So let's look at this diagram. This is the picture of the displacement of Sam. Our friend Sam, will be meeting Sam a lot in this textbook, okay? So Sam started from a position, which is X1, and it moves over time to a final position, XF. What will be the displacement of Sam? You can see Sam here on the start point, where 50 feet in the S direction. Now, Sam covered the distance to 150. What is the displacement of Sam? Okay, I'm seeing the response. Yes, yes, correct. It's 100. We have it. So you see, we can easily say that Sam has covered 100 feet. How were we able to say this? With our understanding of position, time, distance, descriptions of model, right? So we're just looking at the application of this whole motion description into how we can put numbers and units to them, all right? So Sam has covered 100 feet, so the displacement of Sam is 100 feet. Okay. So we have some descriptions that did not have to involve pictures. Like I said, if you have a definition or description that did not have to involve pictures, you can easily make a sketch for better understanding using the model representation, right? So Mara is at position X, 23 meters. She then undergoes a displacement of minus 50 meters. What is a final position? Okay, so let's make the pictorial diagram of Maria. It's at position, and then from this position, she made a displacement of minus 50 from the formula, change to final. They already told you what you're looking for, final position. That means this is initial position, right? So put this one as the initial, put this one on the other end, you have minus 50 meters is equal to minus 50 meters is equal to 23 minus X. X final minus initial, S final minus 23. So let's see what our answers are in the chat. I'm not seeing any response in the chat. Okay, A, right. The answer is A, the answer is A, the answer is A. So yes, simple. Now, from this first diagram, using the Cartesian coordinate, you have 0 to 150, right? If these arrows turn to this side, and you're describing this in the one-dimensional motion on S coordinates, our number line knowledge, this side becomes what? Minus, okay? That is just the description of what we have here, all right? When we said she moved or undergo a displacement of minus 50 meters. It just went in the minus X direction, okay? So the answer is A. Okay, so we have another one. We have two motions. Two runners jog along a track. We have runner A and runner B. The positions are shown at 1 second. That is, each is 1 second time interval. Each point was, we took each of these pictures, these dots, the intervals are 1 second apart. Which of the runner is running faster? Remember, we said that when the distance are far apart, what happens to the speed? And when the distance are closer, what is happening to the speed? So which of these runner is running faster? Let me see our response. Okay, great. Great, 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 great. Okay. Our answers says A. How do we know that? From our understanding of representation of motion diagram, we have that the runner A with a wider spacing at the same time interval is having the more speed, okay? So the same idea. We now have this. We will not just look at the spacing. Look at this technically. Okay, don't just judge with the spacing. All right. We have two runners. They started at the same time and they are finishing at the same time. You know, this thing of bracket first, bracket positions. All right. Fine. When we did the motion picture snaps, we can see that the second runner has more spacing, maybe it has more strides than the first runner, but they started at the same time and they finished at the same time. And the question is, which runner is running faster? Okay, both have the same speed. Yes, both have the same speed, but we can describe that the motion of the runner B of one step is twice the first, but they are going to finish at the same time. Okay, so both of them have the same speed. From our understanding of time and position, if they tell you to take at this second, we can see that our conclusion is that both of them have the same speed. Okay. All right. So our next class will begin with the speed of moving objects. And this will bring us to the conclusion of chapter 1. And then the assignment, I'll tell you the day to turn in the assignment, okay? Sorry, I had to use all the time and I've been the only one talking. Does anybody have anything to say? I'd like you to come on the mic and talk. Don't type now. I want to hear your voice, not just in the practical class. Okay, Kate,
All right, thank you.
you're welcome.
I don't know.
Yeah. Can we all hear Kate? Good. All right. Michael, don't just, okay, if it's not about the class, just say something like, hi, everyone. I just want to hear your voice. You've been hearing my voice since morning. I just want everybody's voice to be
Hello.
heard today. Okay, good. Yep. The next person, just take the turn. Who else is coming on the mic?
Hello.
Hello, good to see you.
Hello.
Hello.
Good morning.
Morning.
Good morning.
Morning. All right. So I appreciate if you just pronounce your name because I'm seeing some names here that might be interesting for me to pronounce. So Jaden, how do you pronounce that? And Amanza, how do you pronounce that? Just say, okay, good morning, I'm Charity. Good morning, I'm Jaden. Good morning, I'm this. Just quickly, let's do that in the next 2 seconds.
I'm Jaden. Good morning.
Good morning.
I'm Guanlin. Good morning.
Good morning.
I'm Kia. Good morning.
Good morning. Jade.
Good morning. My name is Margaret.
Margaret, good morning.
Good morning.
My name is Jade.
Good morning.
Good morning. My name is Madeline.
Good morning.
Good morning. My name is Shay.
Yeah, good morning.
Good morning. My name is Olivia.
Olivia, good morning. Okay. So we have some more persons who has not spoken. All right.
Good morning. My name is Casey.
Kesia, good morning.
Good morning. My name is Ryan.
Ryan, good morning.
Good morning. My name is Caitlin.
Kate one, good morning. Okay, good. All right. So I understand that we'll have some other classes. So I'll just leave you to go for your next class. Have a great day. See you on Friday.
Thank you.
Okay, bye-bye.
Dr. Charity, before I go,
Okay.
when is the lab? Like next week?
Yes, we're starting our lab next week. And on Friday, I'll be posting what you have to read before the class, okay?
Okay,
I'll
thank you.
I'll put it on Moodle. I'll send a message across, but I'll do this for just this time. Every other time, I'll just put it up. I will not put up a message to everyone, okay? All right.
Dr. Charity,
Yes.
I have a lab for physics this afternoon. So you said the lab starts next week. So do I have to
Yes.
show up for today?
Yes, no need to show up today.
Okay.
Lab will be next week.
All right. Thank you. Have a wonderful day.
Thank you. Have a wonderful day.
Thank you.
All right. Tell some of your friends
You
that
Thank you. Bye.
there will not be
I have a-
lab
I
today.
have a question
you.
about
Have
the
a good day.
textbook.
Okay, have a good day. Yeah.
Question about the textbook. I have the second edition. Do I really need to get the fourth one, like you said?
Okay. The only thing about the second edition is when I make references to questions to answer, you have to, if I say answer chapter 1, exercise 10, it's not going to be the same question in edition 2, okay? So you can make use of the edition 2, but get to write, answer the question for the assignments from the current edition, okay?
Thank you.
You're welcome.
Dr. Charity, I got a quick question, if you don't mind.
Okay.
So that assignment you're talking about, was that posted on Moodle?
No, not on Moodle directly. It's in that slide. the PowerPoint or the PDF version. So I'm going to extract it out and post it on Moodle, then emphasize the date you should turn it in. Okay.
Okay. And is the assignment for marks or anything, or is it just like a thing we got to do type thing?
Everything will, in the end, have its score. Okay. So it will be of good habit to do everything we're asked to do, because we can choose the best for you.
Yeah.
All right.
Yeah.
All right.
Okay. So the assignment's in the Moodle, not in the Moodle, in the slideshow. And then you said you're gonna post that thing to read on Moodle for the lab
Yes, I'll
this
post it.
afternoon?
Yeah. No, there will not be lab today. For next week.
Okay.
All right. Lab is going to start from next Wednesday, not this Wednesday.
Alrighty.
Okay.
Okay. Thank you.
All right. Bye-bye. Okay, Chiamaka, I got your message. I hope by next week you'll be out of quarantine, right?
No, I won't.
Can you hear me?
Yes. No.
By next week, you should be out of quarantine. And if you're not by next week, by upper week, you should, right?
No, I won't.
How long is your quarantine?
I have my days left.
Okay, you sent me a message. You can send me a message or email, all right? Okay. Bye-bye. Nine days. Okay, 9 days left. Okay, we'll talk about that later, all right?
Okay.
Yeah. End meeting.